Hi everyone. Today we're going to study proof by strong induction. Strong induction is sometimes known as the second principle of mathematical induction. In here, to prove that the propositional function p of n is true for all positive integers n, we complete two steps. Step 1 is the basis step. In here, it verifies that the proposition P of 1 is true. Step 2 is the inductive step. We assume that P of j is true for j equals from 1, 2, 3 up to k. Then we show that P of the quantity k plus 1 must also be true on this assumption. It proves that the conditional statement P of 1 and P of 2 and P of 3 and up to and P of k implies P of this quantity k plus 1. Let us see this example. Show that if n is an integer greater than 1, then n can be written as the product of primes. Let P of n be the proportional function that n can be written as the product of the primes. Step 1 is the basis step. In our problem, it says that n is an integer greater than 1. So we start with number 2. So we write here P of 2. And P of 2 is true, since 2 is a prime number itself. Therefore, can be written as the product of primes. Step 2 is inductive step, and in here we assume that P of j is true for all integer j, with j less than or equal to k. Let us write examples for this pattern. Let's start with when n equals 2. So 2 is a prime number, therefore P of 2 is true. Now when n is 3, 3 is a prime number, so P of 3 is true. Next, when n equals 4, 4 is a composite number, but we can write number 4 as 2 times 2. Therefore, P of 4 is true. Next, when n is 5, 5 is a prime number, therefore P of 5 is true. Next, when n is 6, this 6 is a composite number, and we can write 6 as 2 times 3. Therefore, P of 6 is true. Next, when n is 7, 7 is a prime number, so P of 7 is true. Next, when n is 8, this 8 is a composite number, and we can write this 8 as 2 times 2 times 2. Therefore, P of 8 is true. Next, when n equals 9, this 9 is a composite number, and we can write this 9 as 3 times 3. Therefore, P of 9 is true. Next, when n equals 10, this 10 is a composite number, and we can write this 10 as 2 times 5. So, P of 10 is true, and so on. To complete the inductive step, it must be shown that P of k plus 1 is true under the assumption. In here, we can see two cases, and those are: first case, when k plus 1 is prime; second case, when k plus 1 is composite. Let us analyze the first case. When k plus 1 is prime, this p of k plus 1 is true because when it is prime, it follows the assumption. Next is when k plus 1 is composite. Then this k plus 1 can be written as the product of two positive integers a and b, with 2 is less than or equal to a is less than or equal to b is less than the quantity k plus 1. By the induction hypothesis, both a and b can be written as the product of primes in the factorization of a and those in the factorization of b. And so we are done with the proof. Just to show an example, let's say k plus 1 is equal to a times b. Let us write some values for a and b respectively. Let's say a equals 2 times 3 times 7, and this b equals 2 times 5 times 7, which means if we write the k plus 1, simply we combine all these factors. So it becomes like this. K plus 1 equals 2 square times 3 times 5 times 7 square.